So today we're gonna finally, I hope, finish our validation of zones, which is a very important part of just creating zones, right? I mean, we can create how many zones we want for any field really, but do they mean something? That's the important part of it. So we have to learn if they mean something, we have to validate them. So I'm just gonna start from scratch as always, opening my own projects folder, and you can do the same on your end as well. Launching that RStudio project icon if yours isn't there yet. Oh, I have a few windows here. Let me just close them so things don't get messed up. Okay, so now launch again here. And so if you already have your script up there for the zone partial, you can just leave it there. If you're not seeing it, again, you can click on that R blue button on your files tab and then come into code, and you should have a zone partial script. So just launch that. It's going to come up on the side. It is possible that you already have all of your objects on the side here. I don't, so I'm going to have to basically recreate them just like we did last time. So I always run the setup chunk because it has all the packages we'll be using. And then for this, actually for this exercise, you can come on the summary chunk if you're following me at this point, and then you can just run all above. And again, we don't want to run the entire script yet because it has some chunks that take time to run, and we actually don't need them anymore because we have already used them to make our decisions. So if you come on the summary one and run all above, that's perfect. And then next step here, we run the all VN chunk. So you can just run that. And then after that, we're just defining number of K. And this is where one of the chunks really takes time. So we really want to skip to that mod KM2 and run that. And then after this point here, we have to run, I guess, all of it. So we have already developed these parts. If you just want to go ahead and run, you can skip the plots. We're not really doing that. You can run the grid. And then, yeah, this is where we stopped. So you can just run whatever we have at this point. So we stopped basically at this map right here. And the question that we actually left off last time was George asking about the boundary and if we lost points close to the boundary. And that was exactly the next step that we were going to deal here. So let's just go through that. Let me just pull up my cheat sheet. Okay, so here in our was everybody able to get to this point? Everybody following? Okay. So we're just I just want to plot here the boundary. So if you recall, I just had a plus after that. We're going to use geom_sf. And say data equals boundary _ W, which is one of the objects that we loaded when we first ran those first chunks up there. And I just want to say fill equals NA so we can see through it and just run that. So George, here's the answer to your question. We actually lost points near the border. And the reason for that is every time that we apply a focal window, like we were explaining on previous class, and just going to pull up again you don't have this script yet, but it's the completed version where I did include some extra chunks to explain that. I just want to show you right here. Again, what is a focal window and what does it do? So this is, what happens is the focal window that we selected had a size of 5 by 5, so 5 pixels in each row and 5 columns of pixels. And what happens is near the border, you cannot really fulfill or complete the entire window with data points because it doesn't have those data points that are outside the boundary. And basically those pixels that don't have the complete set of points within the window, it just assigns an NA. So it is not able to compute whatever we're trying to compute with the window. So that's what's basically happening. So I'm just going to come back here to my partial again. That's what's happening on the border here. Now, let's say, you know, depending on the size of window you're using, depending on the size of the field, this may not be a huge deal. But if you still want to fill in those gaps, there's something we can do here. And does anyone have a guess based on what we've done already in the past? What could we do to fill in those gaps?
Was the function smooth? Was it the smooth?
To fill in the gaps, you mean? But where, like, how would you do that? Like, what function would you use, or? So
but by using buffers?
Buffer, yeah, so the buffer itself, I think it doesn't work in that way because it's more like you're just creating a size around a given shape that you want to extract something, right? In this case, we don't want to extract, we want to create new data points that we don't have. What about interpolation? Right? So that's kind of the answer here. So what we're going to do is interpolate, which is basically just going to fill in those gaps all the way to the border with whatever thinks it makes more sense based on the inverse distance weight algorithm. So I want to invite you to come back to the code right above where we have the plot.
So Leo, just to keep the jargon the same, I've used the term extrapolate with our students when we're talking about going beyond the data. Are we talking about extrapolating here or actually interpolating with data that exists but are not shown?
No, yeah, that's a good point. We're extrapolating in that sense. Yeah.
Okay.
Yeah.
So remember, everyone, extrapolating means when we're going beyond our data points, like what Professor Morari was showing you. You know, we're extending the line beyond known data points. So at this point, we don't have high certainty of what these numbers would be, but we can fill in the maps.
Exactly. Yeah, that's definitely it. Like we're not, I mean, and in this specific case here, maybe like a pixel, let's say, because you would imagine that everything that's cluster one that in red here would basically extend to be pixel one as well. You're not going to have a pixel two near the border and on this east side here because there's no pixel two there. So the algorithm would not guess that it would be pixel two. However, even if there were a cell or more cells that would be pixel two around this the border, I think it would still probably be wise to just turn that small area into pixel one instead, just to make that contiguous shape of the cluster. But that's a good point. Thanks, George. So if you just come up here to the code, let's see, where would we do that? Yeah, okay, so right here, so before that last mutate, so right after this pipe here, just hit return, and we're basically gonna do interpolation like on the fly, kind of. I mean, on the fly, we're still gonna be saving it, but it's gonna be within the pipe flow instead of being its own object as we have done up until this point. So if you recall, the function for that is called gstat, coming from the package of the same name. And then it has an argument called formula that we're going to specify. And the formula here, well, we want to extrapolate. So let me just print zone S at this point so you can see. So we have this column called cluster, and that is what we want to extrapolate. So we come here in this formula, we say cluster till day one, which is that notation that we've been using. And because it is in a pipe flow, I mean, we still have to specify the data argument. So it has an argument called data equals, but because it is in a pipe flow, how do you know the name of all this within the pipe? it doesn't have a name yet. It is not an object yet within the pipe. So the way to specify that is just by placing a dot right there. So that basically tells that whatever is coming into this is going to be, is calling that basically dot. That's like a placeholder for the data argument. Okay, so if you just, so don't add a pipe yet. So let's just leave that mutate hanging there without being connected. If we just run this and then you print zonest, now all that is the result of, is the output from that gstat call, which is just like a formula for interpolation. So at this point, doesn't really mean anything. So if you remember, we have to then use the function predict with the grid to then be able to actually extrapolate, in this case, using IDW. So we use the pipe right after gstat, hit return. So we use predict, oops, yeah, predict, that was gonna work. And then if you recall before, what we were doing is we were saying whatever object that we were saving gstat, that used to be the first argument here, and the second argument was the grid object. Now, because we're using the pipe, everything that's coming before that pipe is coming into here as the first argument of being the data. So we really need to only specify that second argument, which is the grid. And that's this here is the reason why we imported the grid on the chunk above. That is just to do the extrapolation in this case. Okay, so if we just run right there, if you recall, when we predict a gstat object on the grid, it returns a stars object. So this is what we get now. So it'd be a raster that's being extrapolated. I like to use the star objects, but I do prefer to transform them to vector so we can have more control over how we plot it. So I just want to add another pipe there and do again an st_s_sf. So we transform that stars into a vector, into an SF object. And we can just run this. And if we print the zonest just to check what's the result, now we have an SF object with 44,032 rows, which is, or data points, which is the number of cells that we have on the grid. And we have now, recall that the output of the gstat and predict function is this var1 pred, which is the predicted variable. So it always renames the predicted variable to var1 pred. So now what we're going to do is we can now connect our whatever we've done up until here with that last mutate function that we had before. However, notice that now we don't have a column called cluster anymore. This column has been renamed to var1.pred because we did the extrapolation in this case. So I just want to do that. And then at the end, so let's just run this and see what's in here. So we have var1 pred, var1 var, which is the variance basically of this predicted value, which in this case is all in A's because IDW doesn't give you that. The geometry and the cluster S column, which is what we just created on that mutate. Now what I want to do is really only keep the cluster called this cluster_S column. So if you recall, so we add a pipe after that mutate, we're going to use dplyr : select and just say cluster_S. So this is how it should look like at this point.
I have a question.
Yes.
So since we're extrapolating those values, does that play into like standard error or any type of variance? Since we're not sure what those values would be or could be.
No, I mean, it's just really using distance, right?
Yeah.
It's all distance based. And when we plot the result, you're going to be able to see what happened in relation to that boundary. But I mean, it's really just using the distance. So, you know, if you think of it, we already had all the points, like most of the points in that grid. We're just missing the points near the border. So it's extrapolating only until the border. And what it's going to do basically is just use all the points that are closest to the ones that we're predicting,
Mhm.
and assign that value to that point.
Okay, yeah. Okay, that makes sense. It's pulling numbers that are already there and already factored in out and just using them. Yeah. Okay,
Yeah,
thank
but
you.
it does not take variance or any sort of variability into aspect. It's just based on distance.
Right. Okay, cool. Thank you.
Okay, so if we run this and then we print our zonest object, we do have that cluster underscore s column and the geometry. That's all I wanted from this. So let's just come below here on our map and so take a look at what it is now, right? And let's just run and see what happens. Cool. So basically just did that. It just filled in the blanks between whatever we had up all the way up to the border. So now we have, all the points that we needed for these two zones for this field here. Was everyone able to get to this point? Anyone has any questions? Good. All right. So now we basically, this is basically, some of the steps that Dr. Verk did with you guys on Ag Leader SMS. And here it would just be like an automated way of doing this using the focal or the kernel moving average, focal moving average, a couple of different names for the same technique, but that's basically what we did here. And just want to, actually, I think we have that map up here.
So while Dr. Bastos is looking through the code there for a minute, I just want to emphasize something to all of you. The software that Dr. Verk was using, he pressed a button from the individual data points and he created a surface map for him. And that was completely black box, right? I mean, you don't really know unless you investigate what kind of interpolation techniques they use, inverse distance weighting, Krieging, we don't know, right? It's just a black box. Whereas now you have learned two different ways to actually be able to analyze the data and understand how you should take individual data points and make zones out of them. And so this is sort of the scientific method. And I always worry very much when we look at pieces of software like SMS Basic or FarmWorks or whatever, and you just press that button and you have a surface map and you don't really know how valid it is, right? And then people are making management decisions and spreading fertilizer based on that map. So, I mean, it makes me very, very nervous and uncomfortable. And if I was a service provider, I just don't have the confidence that I'd be able to do that. But people just ignore it because it's easy. But you know better now.
Yeah, that's a great conversation because when Dr. Vic was showing like how to create zones, how to do, I guess he was doing interpolation on the go as well. And we had no control over size of grid or maybe the distance we wanted for that interpolation to happen. Like all the parameters that we're able to fine tune here in code, we were not really seeing any of that on SMS. And it's definitely, I guess if you're not really worried about the actual quality of that map, and if you're not going to have to defend your choices in front of anyone else, I guess that could work. But anytime, especially in science, right, we cannot just have complete black box like that. We have to know what's going on behind the scenes. We have to be able to control the results and just the quality of what we're producing. So yeah, I really, I definitely know that Ag Leader SMS has its place commercially. But I guess when we're really trying to understand the ins and outs of something, I guess it has abstracted that complexity so much that we really don't know what's going on. And in scientific setups, it's not really what we want to have. Okay, so what I want to do now is we do have, so this is our final cluster / zone management map. Now I want to understand, the next step here is to understand how each one of the variables that we did use to create these two zones. So if you recall, we used a whole bunch of terrain variables like slope, elevation, aspect, and others. We also use soil electroconductivity at 2 different depths. to create these zones. I want to see so if you imagine like kind of like overlaying all those maps where we have the zones, but we have all of those other layers related to them in a pixel by pixel basis, and really trying to understand how those variables are driving these clusters. So maybe we can understand what is the underlying mechanism that brought about these clusters here. Is it, what is the limitation that perhaps we can manage, or maybe we even cannot manage? But let's just try to understand that. So if you, let's see where I have that. Oh, I actually have a couple more things that I want to do here in this plot before I actually do that. Just want to make this a little bit nicer looking, because the assignment is going to rely on this. So let's just change. So if you want to come back to this plot, just add a plus. I want to change the fill of this plot. So we're going to use scale fill _ colorblind. It should be an option for you coming from DG themes. So if we just run that, it just changes the color for us. The next thing I want to do is add a plus, and we're going to use the function labs to change labels in this plot. In the specific case here, I want to change the title. So we're going to say title equals, and then open and close quotation marks. I want to call this smoothed zones, comma 5 by 5, because that was the size of the focal window that we used, and comma mean, because mean was the name of the function we use in that smoothing algorithm. I want to add a plus. I want to change this theme here to theme map. So it removes theme _ map. So it removes, let me just run this so you can see. So it basically removed the X and Y axis names, and it just also added the title that we specified. And lastly, I just want to add a plus and again call that theme function. I want to change again the color of the title to blue. So with that, we say plot.title. And if you recall, we have to call element _ text to change that. So we say element _ text, color equals, open and close quotation marks, blue. If you run it, this is what we get. And now I want to save this to file, because we're going to need to be looking at these plots again for the assignment. So we do gg save. So notice I did not use a plus there. It's just like its own function by itself. We open and close quotation marks. We need to get outside of the code folder. So .. / you hit tab, go inside the output folder. And I want to call this zone smoothed _ 5x5 _ mean .png. Sorry, I know it's a long name, but we're going to have some different variations of this name. So that's why it has so much information on it. And then I just want to say width of this plot to be 3 inches, comma, and then height of this plot to be 4 inches. So if you just run this entire chunk, and if you, let's quickly here inspect. So click on the R button, go on output, and this was the zone, let's see, zone smoothed 5 by 5 mean. This is what you should have now on your saved on your output folder. Okay. All right, so now we have that. We can move on. And actually, I think here I have one more chunk that I didn't give to you because I made it after the fact. So if you just want to come here on that C+, add an R chunk, we're going to call this zone _s _df. What I want to do now is basically combine the data, all the data that we had for the zones that we use for the zones, all those explanatory variables into the same shape that has the final zone map, which is the one that we're seeing above. So we call this object here zone underscore S underscore DF. That's what I want to call it. We're going to start with the zone underscore S, which is the one that we created with the smooth zones. We had a pipe, hit return, and we're going to use that function st underscore join to join them. And I want to join this with the zone underscore df. And let me just print zone df so you know what it is. It is basically that data set that we use to make the zones, which has all the variables that we use for the zoning. I just want to merge them together. However, we do need to change a couple of parameters here. So the first one is the join type. So we say join equals st underscore equals. That's the type. And if it brings you, if it shows you the opening and closing parentheses like that, you can just delete that. Add a comma and we say left equals true. So if we do this and print it, there will be some NAs here, mostly again related to because the elevation is low open aspect, data don't have those cells on the really close to the boundary. So we're just gonna drop those NA values by adding a pipe there using function drop underscore NA. We run it. I just gonna copy that and paste here so I can print it. So we have back again the 3,700 data points that we had originally on the data that made the zones. Okay, so this is basically what we're gonna be using to validate, because now if you notice, we do have that cluster smooth column, but we also have all of the explanatory variable columns here as well. So we're just gonna do some, basically run some quick models on the fly, understanding if let's say if elevation, for example, is it different, significantly different from cluster 1 to cluster 2? That's what the question we will answer here. So if you come to the next chunk, which now you should have it, we're gonna start with this object that we just created. So zone underscore S underscore df. And I don't remember now if I showed you this. Maybe I did not. But what I want to do, let me just show you the data set again. So we have, all these columns here. Let me actually do this differently. Let me do using a different function so I can pull it up. Okay, so this is the data set that we have. We have this cluster column and all the explanatory variables here. So what I want to do now is basically take like each one of these explanatory variables, and instead of having them like side by side, I want to have them each one below the other. So I have one column that's going to be called value, where we have all the values for all these explanatory variables. But then how do we know which value is which variable? So the function will actually also create another column called name, I believe is what it calls, where it just repeats the name of the variable that is associated with those values. So in the end, instead of having 1, 2, 3, 4, 5, 6 columns for exploratory data, we're going to have one called value, one called name. So that's what I want to do here. And it's just for plotting purposes, really, just to make it easier to plot. So we're going to use a function called pivot underscore longer, because we're pivoting our data set in the long direction. And I want to tell it what to exclude from that pivot. So we say minus, and then we use the C function to concatenate. And what I want to exclude from that are the variables cluster S, and geometry. So let me just run this so you can see what it does. So notice now that it pivoted longer, except for the variables that I asked it not to pivot longer. So now we have this name column and this value column. This is really, it's just a trick, I guess, but it's not something we have to get much into. So now let's plot this data set. Let's add a pipe there. Let's call it ggplot. And within this ggplot call, we use the AES function. And I want to say on the X, I want to have the cluster underscore S column. So on the X-axis, we're going to have 1 and 2, because those are the names of the clusters. And then on the Y-axis, we're going to have each one of those variables separately in a different plot. And that's kind of why we had to pivot the data. It's gonna make more sense in a second here. So now on the y-axis, notice that we don't have anymore like elevation, slope, aspect as a column name. And remember on ggplot, you have to use column names to specify what you want to do. So we're actually going to tell value. So value is going to be the column that we're going to have on the y-axis. And I just want to say another thing is color equals cluster underscore s. That's what I want to do at that stage. Okay, so let's add a plus, hit return. And I want to use a geom box plot. So we're going to be creating box plots for each one of the clusters, for each one of the variables. And I also want to say inside of geom box plot, I want to say show.legend equals false. So show.legend is an argument that will populate for you, just so we exclude this from not appearing as a legend. Let's just run this and see what happens. So if you think of it, all the values within cluster 1 and all the values within cluster 2 are for all of those different variables that we use. So elevation, terrain, and all that. It makes no sense to mix all of them in the same box plot, right? But what I really want to do is have one plot like this for each one of those variables. So the way that we do that is using facetwrap. So we're going to add a plus, hit return, and do facet underscore wrap. I want to facet it by that name column. Remember, the name column is the one that has all the names for all the variables that we pivoted. And then I just want to change a couple of parameters here. So one is scales. So this is scales equals free underscore y, meaning that the range of values on the scale is going to be able to change depending on the variable, not be fixed for all of them. And also want to say ncol for the number of columns equals 3. So if we run this, this is what we get now. Okay, this is a lot better, right? So now what it did is it looked at that column name and noticed it had 6 different names in there, which were the previous variables that we used for clustering, and basically made one plot for each one of those variables, where now we're looking at the box plots for each one of them. So box plot is basically just showing us the distribution of the data. And just by eyeballing it, we can kind of see that, I mean, it looks like ECA at 30 centimeter, 0 to 30 was higher for cluster 2 than 1. The ECA at 90 centimeters was also seemed like it was higher. So the line going across the box plot is the median. So you kind of think of that as the mean of the data set, but it's really the median. Definitely elevation was very different, but in the other ones, it's kind of difficult to tell. So how can we actually put a statistical number on this instead of just guessing, oh, this is greater than that, or are they really different? That's what so normally we would run like a linear model for each one of these variables, look at that p-value, and then that's how we would say if they were different. That is, I guess, way beyond the time and objectives of this course. So we're not going to get into that. This could be another course that hopefully we'll be offering in the future. But what we're going to do is do that on the fly very quickly here without really thinking much about it, just more from an exploratory perspective. So we're going to add a plus here, and there is a function called stat underscore compare underscore means. This comes from the ggpubr package. If you start typing and this function does not appear, is because you have not installed or have not loaded this package. So if that's the case, the name of the package is again ggpubr. I think I had it on that setup chunk all the way up there, but anyways, if you need to install, you know how to do that. This is the name, and then you have to load it using the library function to make this function here available for you. Stat compare means is what we're going to use. And we're just going to change a couple of arguments here. So the first one is called label underscore, no, just label. Yeah, sorry. Just label is the name of the argument. And we're going to change it to p.format. That's what I want to change it. So it shows us the p-value between that comparison. The other argument here is age just for horizontal adjustments. I want to have minus 0.1. And lastly, I want to do change the vertical adjustment to be 1. So these last arguments are just changing how the p-value appears in the plot. And if we run it, it's going to add a p-value of that comparison. So if we notice here, it's kind of hard to see, but all the p-values are like less than 2 to the power of minus 10 or something like that. Maybe the largest one is 0.016. And if you've taken any stats courses, what we're looking for here is anything below, I mean, as a rule of thumb, anything below 0.05, we would say that is significantly different. All of them here are significantly different, right? So we can really see that for all of these variables, they have significantly different values from one cluster to the next. All right, so now we're just going to talk a little bit about this and how can we understand the importance of these variables and what do they really mean for these different clusters. So here's maybe let's just ask here anyone. So if you can look at these values here, I'm just going to pop this out so we can see better on my screen. Let's just have a quick chat here about. So basically, all of these variables are different, right? So let's just take the example of ECA. So electroconductivity, significantly higher electroconductivity for cluster 2 compared to 1, both shallow and deep. What do you think? We're not looking yet at yield, right? So we don't know what this translates into yield quite yet. But what would you expect for this how do you think this would be related to yield? Given just ECA by itself and what we learned about ECA, what does that relate to as far as soil texture, specifically soil texture in this case? Would you expect to have, let's just think about cluster 2. So cluster 2 has higher ECA, both shallow and deep. Do you think cluster 2, because of that, would be higher yielding or lower yielding compared to cluster 1? Victoria, what do you think? Higher? Why do you think that? But then how do you think that relates to yield? So like better fertility, possibly? Okay, awesome. Sven, what do you think?
Yeah, I think it depends because like the ECA is higher when the soil texture is finer, so if it's a higher clay content, what that might reduce it, you know what I'm saying? There's too compacted
Mm-hmm.
saturated water, it may reduce it. But like what you're saying, generally, it's good.
Awesome. And both of your guys' points are right on point. So I don't know if everyone on Zoom was able to hear. I'll just repeat that. So Victoria was saying that she would think cluster 2 would be higher yielding because it probably has better fertility. And Spen was saying that it probably depends because if you have higher fertility, but you also have like a very heavy, fine texture soil, that could be on the other side of impacting yields negatively. And this is when I was going through this, I thought both things as well. And then we're really going to see this when we validate with yield. And that's what's going to happen, what's going to help us to really understand which one is valid for this field. Anyone else has any thoughts about what would you expect, at least based on EC? Of course, we have all these variables. If anyone has any other thoughts about any of the other variables, let's see here. I'm gonna call out Janice. Janice, do you agree with Victoria and Span? Do you have a different opinion?
Yeah, I would go with Span. I remember Dr. Virk said specifically about this field that he had that higher clay doesn't mean also higher yield, because it depends also on other factors. It's maybe we'll have drainage problems, or heavy soils doesn't really benefit the yield. So I think we have to take into consideration more factors than just the structure, the soil properties.
Awesome, awesome, great. And this is, again, it's something very interesting because we're validating at this point only with the variables that we use to create the zones. So we would expect for those variables to be related to the zones because they were the ones used to create them. But now let's use yield, which we did not use to create the zone. So yield is really like a completely, from our analysis standpoint, completely independent from the zone creation. Of course, they're probably related overall, but at least from our creation of the zones, the algorithm k-means did not see yield data. So it does not know how that behaves. Okay, so we're kind of talking about that. I left you here a chunk to bring in this data set that we created on the spatial temporal stability of yield. I left you for you there, so you can just run it. You should be, so if you had followed a similar path and naming choices of what I've done, this would bring the data set easily. If you had any issues, it's probably because maybe you saved in a different folder, maybe your folder structure is different, maybe you saved it as a different name, but hopefully you were able to bring this in. We created, again, this data set at the end of that spatial temporal variability exercise. So I imported this here, just quickly checking, it is on the correct CRS, and it has 4,032 rows. And if you recall, is the one that has low or high for each one of the years, and then combining them into that stable low, stable high, or unstable category when considering all 3 years. So this is what we have. This is what I want to use to validate with yield. So we're not going to use the raw actual, not raw, but we're not going to use the actual absolute yield values. We're just going to use those classes of low or high based here, if you recall. But for us to do that, we have to basically combine this data set with a data set that has the cluster ID column, which at this point, STL does not have that column. So we're going to combine into this object here that I'm calling zone ST. So we're going to start that with our zone data set that we were using above, which is the zone underscore S for smoothed underscore df. Add a pipe, and we're going to use that function st join that we've been using to make spatial joins. And we're going to join this with the st underscore all. And again, we're going to change the same arguments we've been changing. So join equals st underscore equals. You can just remove the parentheses if they appear there. Add a comma and say left equals true. So if we run that, and we run zone st, we see now that zone st, so the product of this join has about 3,700 data rows. And we have now this cluster S column, that's the one that we want, with all those variables that we had already merged. So all the explanatory variables, but also now we have the yield variables coming from STL all in here. Okay, so this is the one that we're going to be using to really validate yield in this case. So what I want to do is I want to build with you a sort of like a contingency table for each one of the years. And we're going to start with 2017. We're going to go very slowly, but we're going to start, with this. So zone underscore ST, which is the one that we just joined with the zone ID and also the yield spatial temporal variability information. The first thing I want to do here is to drop the geometry. So make this to become only a data frame and not an SF object. And you're going to understand better afterwards why we're doing this. But to do that, we're going to use the function st underscore drop underscore geometry. So that would be the first step. If we just run this, you see that now this is only a data frame. Like it does not have spatial information anymore. It's just a data frame. Okay, so what I want to do now is I basically want to, let me see here what I was doing. I want to know how many observations. So really what we need here is the clusters and then these columns here. So we're doing for 2017 first. So I basically want to know how many clusters were low or high yielding in, sorry, I'm using a confusing choice of words. Let me take a step back. I want to know how many low or high yielding data points there were in 2017 that fell within zone 1 or zone 2. That's what I want to know. I want to know that proportion. So to do that, we need to do a group by. So let's just do a pipe there. We're going to group by initially by clusters underscore S. And if you recall, when we just do a group by doesn't change anything at that point. It's what you do after the group by that really makes a difference. We're going to add a pipe and use the function mutate. Because for us to know proportion, we have to first know the total number of observations that fall within a cluster. So that would be the total number of observations in the cluster. So for this, we're going to do n and capital or uppercase N. I'm going to call the function length, and we're going to give it the clusters underscore S. So that's what I want to do. First, I want to know, let me just, oops, I got an error. What's going on? Oh, clusters, cluster. There we go. So it basically, what it did is it did not decrease the number of rows, but what it did is it looked at each one of my clusters and it told me what was the total number of pixels within each cluster. So now we see here this number, and it's basically going to repeat the same number whenever we are within the same cluster. So basically this N, capital N column has two values, two different values. I mean, it has 3,700 values, but they're repeated in a way that we only have two unique values. So one is 1778, that's for cluster 1. And let me just see if we can, okay, oh, there was a cluster 2 there. Okay, a few clusters 2 here. So if I just come on the side, this should be a different number. Yeah, so cluster 2 has a total of 19,700. This number here for as far as number of pixels, and cluster 1 this number. So they're slightly different in number of observations. But now that we have the total number of observations within the cluster, I want to know of that total, how many were low, how many were high yielding in 2017. So we're going to do another pipe here, and we're actually going to have to do a little bit more complex group by, where we group by cluster as before, but also by S and yield 17. So now it's going to look at all combinations between cluster and S and yield and give us the number of observations. Now we add a pipe here, and instead of using a lowercase n and length of cluster and S and yield, we can just use the function tally. So if we do that, this is the result. So tally basically looks at the combinations that you set up on your group by level and just tells you, creating this column lowercase n, how many observations you had. But one thing that happened here is that capital N, so the total number within a cluster, went away. If we want to keep that, we just got to come back here on this last group by and add that capital N right there and run it. So now we have that capital N right there, and we can basically do a ratio of lower N, capital N, and really know what's the proportion of high and low yield data points within each one of the clusters. Okay, so let's just quickly do that here. We had a pipe, we're going to do a mutate. I want to call this prop for proportion. So we're going to say the prop is, if you want to go ahead and open and close parentheses, I want to do lowercase n divided by uppercase n and multiply this by 100. Oops, not 200. And if we run this, we get the proportion as a percentage. So for example, for cluster 1 in 2017, 32% of the pixels were classified as high yielding and 67 as low yielding. And cluster 2 was kind of the opposite. So most of them were classified as high and 30% as low. Let me just tell you something here. It is possible that for you, the numbers are flipped. Like, for example, in my case here, 2017, cluster 1 had the majority low and cluster 2 majority high. It is possible that for you it's flipped. And the reason is because k-means has a random component to it when generating the initial values. And it is possible that we all got to the same result, but perhaps on your k-means, it's calling cluster 1 as 2 and 2 as 1 when compared to mine, just because of that randomness of the algorithm. But we should have gotten to the same result. So if you're seeing a very similar proportions, just flipped from 1 to 2, that's totally normal. And let me see here. Yeah, let's do this. So I was going to develop further the code, but I just want to finish this, and that would probably take another 5 minutes. I don't want to hold you back for that long. So let's just add a pipe. And instead of us going through and doing this line by line, I just want to invite you to come lower here and copy everything you see starting at ggplot. Okay, so you can just copy that, go back to the 2017 and come on the line right after that pipe and just paste it. And really the only thing that we're going to change that we have to change in this code is just here on the X, we want to say that S and yield 17. That's really, oh, and on the fill as well. So X and fill need to be S and yield 17. Okay, so we're not going to go through much of the code here of the plots. You can check yourself if you're curious, but it's things that were done in the past. So nothing groundbreaking, except that my code didn't work. Let's see what's going on. So I'm going to troubleshoot quickly here. I don't know what's giving me this error. I'm going to stop the workflow right before getting into the ggplot and just see if I have the columns that I'm specifying here. Yes, I have that. So once I see that is correct, I'm going to cancel just the plus of the ggplot, see if it runs here. It runs. I'm going to do that continuously going down. Okay, works. And see what's going on. Where am I getting that error? Oh, okay, I think it's probably on here. Because right now I have cluster and it should have been cluster S. So if I run up until here, that's probably where it breaks. Yep. Okay, and that's because we don't have a column called cluster, we have cluster underscore S. So please go ahead and change that. And now it should work. Okay, these numbers are really ugly. What I want to do quickly here is on the prop. So this proportion here is what those numbers are. I just want to use a function here called round right before the prop. So round prop, comma 0, and then close parentheses. That would be our quick fix for this. So we're just rounding on the fly that number. Let me just, okay, I'm just going to give a moment here on the ggplot side. And while you're catching up with the code, I just want to walk you through what's going on here. So basically we took those numbers and we create plots. I'm a huge plot person, so I like to see plots better than tables. So what we're seeing here is for me, again, this for you could be flipped, but for me, cluster 1 had 68% of low yielding data points and cluster 2 had 69% of high yielding data points. Okay, so now we're validating our clusters with yield data. And in this case, again, not absolute yield, just relative to the median that we classify low or high. So based on at least, and remember, this is for 2017 only. So for 2017, it seems like cluster 1 was low yielding, cluster 2 was high yielding. And if we just go back here to see the plot, so cluster 1, low yielding. So low yield on this east part of the field, higher yield on the west part of the field. Okay, I think we can stop here. I don't want to keep you guys for much longer. But what we're going to finish to do next class on the validation is doing this again for 20. So this is just 2017. We're going to do for 2019 and 2020. And then also do for the spatial temporal component of it, which is going to be really interesting. I'm really looking forward to having that conversation with you guys and see what you think of how we can handle that. Okay, we can wrap up here. Next class, we will for sure finish this because we don't have too much more going on. And then we're going to start the variable rate nitrogen exercise. I think is also a very exciting one. It has very practical conversations and just how we get to the numbers and how we define things. And I'm really excited about that. After that, probably Friday, we'll go through the profitability map. And then after that, I'll give you the final project, which basically going to ask you to redo all this with a new data set and some new challenges as well.
It may be kind of obvious now why a fertilizer company may choose just to push the button on SMS basic, huh?
Yeah, that's true. Yeah, yeah. Anyone has any questions before we go? Anyone on Zoom? All right, well, I guess I'll see you all Wednesday and let me know by email if you have any issues. And thanks. See you then.